Hello everyone and welcome back to my channel. This is going to be the long form video for this RAG application using the religious scripture of Gita, that how you can avoid hallucination of the LLM model and the minimum viable RAG application that you can develop and run it locally on your system without using any API. All the required code for this application, you can find it in my GitHub. This is the Llama RAG IPYNB file and this app.py for the Streamlit app. So firstly, we are going to load our large language model. In this case, I'm going to use the Llama 3.2 3 billion parameter model. And there is an important thing to note during this loading process, and that is firstly, you can use the default version of weights, which is BF float 16, which the model is trained on. So let's see what happens when we load in this config. So when I load in this config, my model is about 5.98 GBs, which can be a little more who just have a normal GPU. What we can do is we can take advantage of bits and bytes config. So what they offer is that you can, instead of 16 bits floating point, you can use 8-bit precision and without much loss in the performance. So let's do this. So for that, what we have to do is we have to create a config. We have to initialize a bits and bytes config. So load in 8-bit is good. This is all we need. And then we have to pass it here. When we are loading the model using auto model for causal LM, here we have to pass this config. You see our model immediately become 3.35 GB. So which is pretty less. You can also, even if you have a 4 GB GPU, which is pretty standard these days, you can run this model. But we can go one step ahead. Instead of 8-bit quantization, we can also do a 4-bit quantization, which will further reduce the size of our model and the VRAM capacity we need. See, finally, the model which we had initially at around 6 GB, it became 2 GB. But one thing to notice here is that this reduction in memory, this only work if you have a GPU of recent CUDA architecture. If you have an older CUDA architecture, this may not work well. With that, we loaded our model, and we have to do two things, because usually this pad token in both in the tokenizer and the model are not initialized. So we manually initialize them. Otherwise, it gives us a warning. It will, if you don't do this also, it will work, but it just throws a warning. So not to have that warning, I manually assign them. So before loading the model, my GPU utilization is 1.2 GB. Let's say how much it is after I load the model. Yes, after I load the model, it's around 3.5 GB. In the next step, I'm going to use the PDF file of the Gita and use the PyPDF reader. Just for the note, here you can totally use the LangChain functions, which are way more easy to use, but I'm making this for absolute beginners. So I wanted to first stick to manual implementation, then I will go to library implementation so that I can understand what is going on underneath it first. Let me give you a look at what this PDF looks like. It's basically an English translated version. It has all the 18 chapters. Thank you authors for making it publicly available. So I use the PyPDF 2, and from there I use the PDF reader for method, and I pass the path. All this PDF is now read and saved in this PDF reader object. I can do like PDF reader.pages, and it gives me how many pages are there. Here there are 53 pages in this. And one thing to notice here is I'm going from 4th page onwards until the penultimate page. Why is that? Because if I show you the Gita, see, so this is the first page, second, third, fourth. So until 4th page, it's just the index. So I don't need to put the index in my RAG file. Otherwise, it will just take unnecessary spaces. And maybe while retrieving, it will just retrieve some chunks from here, which means nothing. So that's why I'm not including the first 4 pages and the last page, because last page there are credits and everything. So this page basically, so extracting text from all these pages and putting them in this full text variable. So if I run this, it's pretty fast. It didn't even take 1 second. So now let's see what this full text looks like. So you see, it took all the corpus of text, but there is one problem here. The main problem is because when we read from a PDF, there are often inconsistency in the word that it extracts. For example, here, you see, this is self-knowledge. There shouldn't be any space in between. Also, actually, there is a line break here. So instead of print, if I just so here you see so many unnecessary line changes there. You know, like everything also is not one word, because sometimes it happens that towards the end there is EVE and then RYTHING. So it just thinks when extracting the word from there, it thinks both are different words. So these are problematic when you do RAG because they do not make full sense. So here you have two options. Either you manually correct them, either you go through your text and manually correct them, or we can take advantage of a large language model that we already have here. So this was the process of extracting the data from the PDF. And next we'll move on to our next step, which is chunking part. For the chunking part, I'm taking a very simple approach of fixed length based chunking. So in there, what we do, we predefine a chunk size, let's say 100 tokens. In this example, I'm taking tokens instead of a character, and I'm taking a chunk overlap of 20. That means for the first chunk it will take 1 to 100, and for the second chunk it will take from 80 to 180, so on. And so there will be an overlap between chunks, and that's what I'm doing. I'm just running a for loop from this tokenized text. Let me just show you what is this tokenized text. So this tokenized text is nothing but I pass all the text through my Llama tokenizer, and it converted into corresponding numbers. If I write here len, you see I have total 34,000 tokens. We run this and we see that after that we get total 431 chunks. Let me show you how the chunks look like. Here is the chunk list. Many chunks there. Let's look at a random one. Let's say 10. See, this is how the chunk looks like. And of course, there are irregularities like the chapters or something like this. So I'm not going to do it manually. Instead, I'm going to use the language model I already have to clean this kind of text. So yeah, this part comes there, cleaning each chunk so that the language model can comprehend and make sense of whatever is there in it. So for that, I created, I prompted this, the same model, in fact, the same Llama model, but I'm asking it to act as a text cleaner. So here I'm saying that you are a text editor that refines extracted text while presuming its meaning. Your task is to clean up the text by removing any unnecessary line breaks, removing page numbers, stripping out any other irrelevant and redundant information, and give me the text itself. So, and in this function, what is my input is this text, which is like unedited or raw text, something like this. So let's see what happens. So before it was like this. So there were a lot of unnecessary line breaks here. You see chapter, advice, and now this is the clean text. So it cleaned it pretty well. Now there is no unnecessary line breaks. And this is a very good way, but it takes a lot of time because you have to run the large language model for each chunk, and you have 400 chunks, so you have to run it 400 times. For me, it took around 20 minutes to run it on all my entire this chunk list. And after that, what I did, I pickled them. So for now, I'm not gonna run it again. I'm just gonna read it. And now let's see the clean text. This is the clean text you got, and here let's say. See, so this is my clean text. There is no unnecessary line breaks. And now what I can do is I can encode them, because right now I have to create my vector embedding or the vector embedding database. But before creating the vector database, let me tell you about this model, the model I'm going to use. So for this, I'm going to use the sentence transformer library. This is the documentation of the sentence transformer library. It's basically an extension of Hugging Face, where you can do like a lot of RAG implementation and converting sentence to embedding pretty easily. So for here, we're going to use this pre-trained model. And yeah, here you can see that how you can use all this model. It's very easy and very intuitive. And they have a lot of model along with their score. So right now I'm using this model because it's pretty small in size compared to this all MPNet base is the highest accuracy, but its size is also pretty big, like 420. Right now I'm using this all mini LM L12, which is like very close in performance to this one, but at the same time it has like 25% of the size of the bigger model. I also use this one also, it works pretty well. So yeah, you go depending upon your need, whether you go for higher accuracy or lesser memory. So now I will load this pre-trained model. For that it's very easy, sentence transformer, and you pass the name of the model that you want to use, and that is your embedding model. So just to demonstrate that how this sentence vector space looks like, so I created I prompted ChatGPT to create me example sentence. So here you see there are 3 sentences about programming, then there are few sentences about daily activities, then there are 2 sentences about artificial intelligence, AI, robotics and all. And after that what I did, I passed this all the list of sentences into my embedding model.encode function, and I got the embeddings here. Now you see, for each sentence I have a vector of 384, and as I have 8 total sentences, I get a matrix of 8 rows and 384 columns. But I want to project them and visualize them in a 2-dimensional space. So that's why I'm going to take advantage of UMAP. UMAP and t-SNEs are 2 very popular methods. Even you can use PCA for that matter to project high dimensional space vectors into a 2-dimensional or 3-dimensional space. And yeah, so right now we see that all the sentences related to Python are grouped together, artificial intelligence and robotics are grouped together, and daily talk are grouped together. So that means that the sentence encoder that we have, it is pretty effective, and it can semantically create representative vectors for each text chunk that will help us find similar character in the from our vector database. So yeah, so now what I did is I used the embedding model.encode function, but now I used it on my cleaned text. So this has like 431 chunks extracted from the Gita text. I'm asking it to convert it into PyTorch tensor, and there I'm normalizing the embeddings, and then I'm saving it as vector embedding.pt so that when I'm doing my inference, I can directly load this vector embeddings.pt, and I do not have to create this vector embeddings every time. It doesn't take much time here because I have very few samples. So now let's try to retrieve some text from this vector database. So this embedding tensor itself is our vector database. There are other more advanced way to create this vector data. So for example, let's say I have a question that I struggle to control my anger. What can I do to remain peaceful? Of course, this exact sentence is not present in the text of Gita. I want to retrieve the chunks. Those are somehow semantically related to this one. So for that, what I will do, first I will encode them, encode this particular text and get my query encoded vector. And then I'll use, in the embedding model, there is a similarity function. So what it does, it takes my query vector and the embedding tensor, which is the embedding of all the text in all the chunks of text from Gita. So now I'm just commenting out and just to see that what it gives. So now let's see what is the similarities. You see, this is basically a tensor, and I write dot shape. All right. So 431 is the number of chunks we have. and it gave us the similarity with respect to each chunk. Now my goal is to find the indices of the chunks that it has highest similarity with. So for that, I'm using torch.topk function, and I'm notifying it how many top nearest neighbor I want. So you see, this is the corresponding similarity score, and this is the indices of those chunks inside my cleaned text. Now putting all of them together, I see that, okay, this particular chunk has highest similarity 0.5. This is chunk number 58, and it says the anger comes from unfulfilled desire, delusion, or wild idea arises from anger. It's something in the similar line that I struggle to control my anger. And also, I think, yeah, it goes in less from highest relevance to lesser relevance. Here, I need to tell you that this is not the only way we can do, because here we do a semantic. When we use an embedding model, we are basically doing semantic based similarity searching, but we can also do keyword based similarity searching. For that, something called BM25 is used. It's TF-IDF plus normalized according to the length of the sentence. In the upcoming videos, because this video is not the end, I want to, because this is the bare minimum implementation of RAG, but I want to take this further. I want to create a full implementation of RAG which can be deployed on just like ChatGPT. So if you are interested in learning more about RAG and all the advanced techniques in RAG, don't forget to like and subscribe to this channel. With that said, let's see here. So we got all the relevant chunk of text we wanted. Now we'll just put them together into a single sentence. So for that, I'm using this. So in this line, I'm just gonna join all the text I extracted, the most similar text to my question, and I'm put them in my context text. So you see, my context is now just a bigger chunk of text, which is just the concatenation of all them. And now comes preparing my message or the conversation that I'll pass it to my large language model or Llama model in this case. So first I will add the query. In my case, the query is this. And then this is my prompt. So which says that you are a compassionate guide. You answer question based only on the given context of Gita and do not add any extra information. Code the text you have used from Gita context. If the question asked by the user is not related to the context, you say this is not related to Bhagavad Gita. Your goal is to first interpret the writings of Gita in a given context and then try your best to relate to user's query. Answer in simple English that a 15-year-old can understand using your interpretation of the given text. And then I pass my context. And I also mentioned that answer shouldn't be longer than 100 words and do not use markdown format. Double this particular sentence in my prompt and it now quotes more often than it doesn't. So this helped, and it kind of took me like 5-6 iteration to come up with this prompt. And then I used my tokenizer.apply chat template. So all these things I've already explained in my Llama introduction video. If you have not watched that till now, please give it a chance. And then it's very simple. I just pass it through the model, then it's my output and I print my output. So let's do that. So this is the answer given by Llama model in the context of Gita. To remain peaceful, you should control your senses and bring them under your control. This is because anger comes from unfulfilled. And also it quotes the part. But you can go even one step forward. That, not only make it write your answer, but you can make it speak your answer as well by attaching a text to speech model after that. So I'm using the Kokoro model. I've explained Kokoro model in detail. You can follow the entire video where I showed how you can automatically convert from a PDF to a podcast. So I initialize my Kokoro pipeline and call it TTS pipeline, and then I pass in this the processed text from the LLM model. And there are a lot of options for what type of voice you want to use. So your HM means Hindi male, and there are like 2 options for that.
Remain peaceful. You should control your senses and bring them under your control. This is because anger comes from unfulfilled desires and delusion arises from anger. When your senses are under control, your mind becomes steady.
So yeah, that was the very simple way of how you can use this. But this is, we did everything on a Jupyter notebook. So what I did is I put all the required method for this RAG implementation in one function. It's not a big function, you can see here. And it returns an audio file directly. But it's not necessary. You can just, comment this out and just pass the processed text as your return. And I created a Streamlit app out of it. You can find the Streamlit app. It's called app.py in my GitHub repository. Just a brief walk through the Streamlit app. I imported all the necessary libraries and then I use the cache resource. That means once I load this model, so what happens with Streamlit is each time you press a button, the entire page is loaded. So if you do not cache the memory, the model, it needs to be cached. It will be loaded every time you press any button or you interact anything with the Streamlit app. So for that, I'll load my model and yeah, it gives my model and tokenizer which do not change. It does stay cached as long as you do not close the tab. Also my embedding model, I cache them. I also cache my vector embedding as well as my cleaned text file, because from the vector embedding I load the clean text. All right, this is the loading part. The actual loading happens here. And then the function that I showed before, rag Gita function, it just takes the query as input and it gives the processed text as output and also the context it has retrieved. So, and here is the entire implementation of the app, by the way. Nothing is very simple. Just the title and this is a text area to give your query. So now let's see how does this look in real life. The app.py, you have to come to your command line and just write streamlit run. And now it's loading the model and the embedding and the list of chunks that we have. I put a default question and now let's do get answer. See, so now it gave us the answer. Hello there, I'm here to help you understand and everything. It gave the answer and also it gave the context from the Gita that it has retrieved. So for example, if you search this code to, to validate the sanity of this model, whether it is hallucinating or not. So it is unborn, eternal, permanent and primal. The spirit is not destroyed when the body is destroyed. So everything, this particular part is quoted from the actual Gita verses. Now let's change the sentence to see whether our caching part works or not. So now you see at this time there was no model loaded. And now we get another response and a different context as well. So that was all about this video. In the upcoming videos, I'm going to show the advanced methods on the same use case so that you can get an understanding of how adding advanced components to this particular RAG pipeline can improve the performance. In terms of advanced RAG methods, what I can think of is we can definitely improve the chunking part. We can also improve the retrieval from the PDF, because right now we are just using the PDF reader and it may not be the best option. The sentence encoder we are right now using is pretty generic. And if you want the best performance, we need to fine tune the sentence encoder on our own text so that it knows the context of our text very well. And if all this part interests you, then do subscribe to the channel. Until next time, stay curious.